In this problem, we will talk about tangent lines to polar curves. Specifically, we will find the points on the curve r equals 3 minus 3 sine theta, where the tangent line is horizontal or vertical. In order to look at the derivative dy dx using polar coordinates, we need to look at the fraction dy d theta divided by dx d theta. And we know that a tangent line is horizontal if the derivative dy dx equals 0, which means that our derivative dy d theta must equal 0 and dx d theta must not be 0, of course. Similarly, we know that we have a vertical tangent line if the derivative dy dx is undefined, which means that the derivative dx d theta in the denominator of the derivative dy dx is equal to 0, and the top of our fraction dy d theta is not equal to 0. So first, let's think about the derivatives themselves. We know that r is equal to 3 minus 3 sine theta. That means that y is equal to r times sine of theta, or in other words, 3 minus 3 times sine theta times sine theta. Distributing, we get 3 sine theta minus 3 sine squared theta. That means that our derivative dy d theta is equal to 3 times cosine theta minus 6 sine theta times cosine theta, using the chain rule for the second term. Now we can set dy d theta equal to 0 and solve. We get 0 equals the derivative dy d theta. I will factor out 3 cosine of theta. Setting each factor to 0, we see that either cosine theta equals 0 or sine of theta equals 1/2. If cosine theta equals 0, theta must be pi over 2 or 3 pi over 2 or any angle coterminal with one of those. And if sine of theta equals 1/2, theta must be pi over 6 or 5 pi over 6 or any angle coterminal with one of those. Now let's look at the derivative dx d theta. We know that x is equal to r cosine theta, or in other words, 3 minus 3 sine theta times cosine theta, or 3 cosine theta minus 3 sine theta cosine theta. So our derivative dx d theta is negative 3 times sine theta minus 3 sine theta times negative sine theta minus 3 cosine theta times cosine theta, where I've used the product rule for the second term. Simplifying, this gives me negative 3 sine theta plus 3 sine squared theta minus 3 cosine squared theta. So setting the derivative dx d theta equal to 0, we have 0 equals that derivative, negative 3 sine theta plus 3 sine squared theta minus 3 cosine squared theta. However, instead of writing cosine squared theta, I will use the Pythagorean identity and write this as 1 minus sine squared theta. Simplifying the right side and collecting like terms, we get 6 sine squared theta minus 3 sine theta minus 3. Now I can simplify a little bit more by dividing both sides by 3. So 0 equals 2 times sine squared theta minus sine theta minus 1. Factoring, I get 0 equals 2 times sine theta plus 1 times sine of theta minus 1, which means that sine theta is equal to negative 1/2, or sine of theta equals 1. If sine of theta equals negative 1/2, theta is equal to 7 pi over 6, or theta is equal to 11 pi over 6, or any angles coterminal with those. And if sine of theta equals 1, then theta equals pi over 2, or any coterminal angle. Let's recap. So far we have determined that dy d theta is equal to 0 if theta equals pi over 2, 3 pi over 2, pi over 6, or 5 pi over 6, or any angle coterminal with one of those. And dx d theta equals 0 if theta equals 7 pi over 6, 11 pi over 6, pi over 2, or any coterminal angle. We know that we have a horizontal tangent line if dy d theta equals 0 and dx d theta does not equal 0. We see that dy d theta equals 0 if theta is equal to 3 pi over 2, pi over 6, or 5 pi over 6. We are not including pi over 2 at the moment because at pi over 2, both dy d theta and dx d theta are equal to 0. So theta is equal to 3 pi over 2, or pi over 6, or 5 pi over 6. Now, because we need to find the points on the curve, we also need to find the r value for each of those values of theta. So if theta is 3 pi over 2, r is equal to 3 minus 3 times sine of 3 pi over 2. Sine of 3 pi over 2 is negative 1. So overall r equals 6. If theta is equal to pi over 6, r is 3 minus 3 times sine of pi over 6. Sine of pi over 6 is 1/2. So r is 3/2. Lastly, if theta is 5 pi over 6, r is equal to 3 minus 3 sine of 5 pi over 6, which gives us 3/2. So we have a horizontal tangent line at the point 6, 3 pi over 2, at the point 3/2, pi over 6, and at the point 3/2, 5 pi over 6. Now let's talk about vertical tangent lines. Recall that we have a vertical tangent line if dx d theta equals 0 and dy d theta does not equal 0. This happens when theta equals 7 pi over 6 or 11 pi over 6. Again, because we need the points, we will plug each of these theta values into our original equation. If theta equals 7 pi over 6, r equals 3 minus 3 times 7 pi over 6. Sine of 7 pi over 6 is negative 1/2. So r is equal to 9/2. Similarly, if theta equals 11 pi over 6, r equals 3 minus 3 times sine of 11 pi over 6, which again gives us r equals 9/2. So our curve has a vertical tangent line at the point 9/2, 7 pi over 6, and at the point 9/2, 11 pi over 6. Now we have one more piece to worry about, and that is what happens at this angle pi over 2, where both dy d theta and dx d theta are equal to 0. To answer this question, let's look at the expression for our derivative. dy dx is equal to dy d theta divided by dx d theta. Using the expressions we found on the first slide, we get 3 sine theta minus 3 sine squared theta divided by 3 cosine theta minus 3 sine theta cosine theta. In order to figure out what happens when theta equals pi over 2, let's instead think about what happens as we take a limit with theta approaching pi divided by 2 of this derivative. Remember, plugging in pi over 2 will give us 0 on the top and 0 on the bottom. So we will use L'Hopital's rule. By L'Hopital's rule, this is equal to the limit as theta approaches pi over 2 of the fraction 3 cosine theta minus 6 sine theta cosine theta divided by negative 3 sine theta plus 3 sine squared theta minus 3 cosine squared theta. Now, if we plug in pi over 2, we will again notice that we get the indeterminate form 0 over 0, which means we can use L'Hopital's rule again. Taking the derivative of the top and bottom of this fraction a second time, we end up with the limit as theta approaches pi over 2 of negative 3 sine of theta plus 6 sine squared theta minus 6 cosine squared theta, all divided by negative 3 cosine of theta plus 6 sine theta cosine theta minus 6 cosine theta times a negative sine theta. Now if we plug in pi over 2, we get negative 3 times sine of pi over 2, which is 1, plus 6 times sine of pi over 2 squared, minus 6 times cosine of pi over 2, which is 0 squared, divided by negative 3 cosine of pi over 2 plus 6 times sine of pi over 2 times cosine of pi over 2 plus 6 times cosine of pi over 2 times sine of pi over 2, which all in all equals 3 divided by 0. We know that 3 divided by 0 is undefined, but this calculation tells us that this limit is infinite. Because our limit is infinite, we know that as our angle theta approaches pi over 2, the derivative, or in other words, the slope of the tangent line to our curve approaches infinity. That means that our curve, r equals 3 minus 3 sine theta, has a vertical tangent line at theta equals pi over 2. Again, to get the ordered pair, if theta equals pi over 2, r is equal to 3 minus 3 times sine of pi over 2, which is 0. So we have a third vertical tangent line at the point 0, comma, pi over 2. Just to recap, we have determined that our curve r equals 3 minus 3 sine theta has a horizontal tangent line at the points 6, 3 pi over 2, at 3 halves, comma, pi over 6, and at 3 halves, 5 pi over 6. We can see from our graph that these 3 points do indeed show that the tangent line is horizontal. We have also determined that our graph has a vertical tangent line at the point 9 halves, comma, 7 pi over 6, and at the point 9 halves, 11 pi over 6, as well as at the pole. So we can in fact see that our graph has a vertical tangent line in these 3 locations.